And thank you for your patience. Just need to get a stick to change the slides. Thank you. Okay, well, thank you again, and thank you so much to the organizers for organizing this conference. It's been very, very interesting to see these topics discussed in several different ways. And my topic today is going to try to also talk about some connections between fluid motion in the quantum sense and in the classical sense in a couple different ways. So, my topic is vortex liquids in phase transition equations, and I'll try to motivate those two things and explain a bit about the results. So I should say that this is joint work with Matthias Kurtzke in the first case and Robert Gerard from University of Toronto in the second case. So I want to talk first a review. So we're all experts here, so this is going to be a bit of a review. Talk about fluid equations and vorticity, which we all understand, at least in a two-dimensional case, is the fundamental way to think about fluid equations in the incompressible case. Then I want to move on and talk about vorticity, again, as we've seen in many cases, in regards to phase transition equation and vorticity there, and the differences between the two things. And then I want to talk about vortex liquids, which is kind of a limiting case of these objects. Okay, so this is our starting point is the two-dimensional incompressible Euler equations, which we've seen, and as we know, it's a challenge to recover the velocity from a given profile. To recover both the velocity and the pressure from a given profile. So typically we work with a vorticity formulation in two dimensions. But one important thing is that we see in a lot of experiments that vorticity tends to concentrate in small lumps, and they themselves have some coherent structure, and they're advected typically by the flow itself. And so here we see, again from the Eindhoven lab, a numerical experiment where we see a lot of localized structures. These are our local eddies or swirls, and we can think about that as sort of approximating very strong currents. But one important thing about the incompressible Euler equations is that we can recover the velocity from the vorticity by the Biot-Savart formulation. So we know in two dimensions that vorticity is advected by the flow, and the flow itself can be recovered by a singular integral operation. And so an important thing is that if you look at the characteristics where the characteristic is driven by the fluid itself, then the vorticity is conserved, right? This is the fundamental feature about 2D incompressible Euler equations, and this is here the particle at a particular point is driven by the fluid. So this is an important thing. And so if you put in your localized vorticity, at least in a formal level, and these lambdas are any real number, and you consider them located at some point aj, then we can track the point aj by these two simple relationships, right? The point is advected by the fluid, and the lambdas are constant along the advection. And so here, the velocity then is recovered by the Biot-Savart formulation, where omega now is a bunch of delta functions with weights, right? And so, at least on a formal basis, we can recover the Helmholtz-Kirchhoff-Onsager ODE, right? So, formally derived by lots of different people. And we get this beautiful relationship. These ODEs are given by this relationship right there. So this is known in the computational community as a point vortex method. Okay, so some questions whether it's really that useful, but it is a very beautiful relationship. And what you can do is if you want to basically model 2D Euler equations, you can, for instance, take a big square fluid. Let's say your domain is like this. You can divide it up into some squares. Let's say that they're pretty small. This is my domain omega, and then I can, on this square, just average the amount of vorticity, and then stick a delta function right in there, right, with the weight that's given by the average of the vorticity on this small square. Okay? And so, so that would be my initial data for my, let's say, vortex n right there at point AJ. And so these are small squares. Let's say n is very large. And then we can ask what happens as you advect it. Well, the question is there some consistency as these squares, as you get more and more of these squares for my domain, as n gets really, really big? Well, you know, first of all, that the vorticity is going to converge to some vorticity measure in measure. But in fact, if the vorticity, let's say, is all positive or all negative, then in fact you can get that this is, in fact, converges to a weak solution to the Euler equations. This is a famous result of Delors and Chauchet, combining a couple different things together. And so this is kind of an unusual way to think about the Euler equations, but it's some way that allows you to pass to the limit. And I'll talk a little bit more about this later on. So here we're using, at several levels, the Biot-Savart formulations here. Uj, again, is recovered by singular integral operator acting on the vorticity formulation. Okay. Okay. So the convergence on this right-hand side is non-trivial. This was done by Chauchet for this point vortex method using methods of Delors, and there are also alternative proofs by Maida and Evans-Mueller for data that's in measure, but also a little bit better. That's an H-1. So vortex sheet initial data. So there is some consistency. And some of the primary issue why it didn't follow so easily is that, in some sense, K convolved with the singular integral operator acting on omega that recovers the velocity doesn't perform well in L1. Okay, and that's basic Calderon-Zygmunt theory. You have to be slightly better than L1 or slightly worse than L infinity. Instead, they use some nice compactness methods, and in the case of Evans-Mueller, they use the Hardy space BMO duality. Really beautiful results. Okay, so that's in the Euler equations. I want to now try to make a connection with problems coming from phase transition equations. So we've seen this, especially with the lectures of Leah. There is, in the phase transition equations, at least for a complex order phase transition equations, a complex order parameter U, which gives us a complex number, and that, in the local average sense, gives us what the state is of the system. It could either be in a super state, which we'll talk about in a couple of different settings, or in a normal state. But because it's complex value, there's an additional piece of information, which is very important to us, and that is the direction, this phi. Okay, so it's not just a scalar. There's something else. And in a lot of cases that are physical interest, for instance, in the Groth-Spidovetsky equation, there's a Hamiltonian associated to, let's say, the equations, which I'll write up in a little bit, and that energy is of this form, and has been studied, for instance, by Boiteux, Brézis, Hélène at the initial stages, along with many other people, and Leah also gave a lot of background on this. And you hope that there's some type of reasonable decay at infinity. Again, the fundamental object that we're interested in are things called vortices, but in this case is in the quantum mechanical sense. So here, in our setting, a vortex can first be thought of as a region where the superstate drops out of its special state and goes into the normal state. And so that would be, for instance, let's say when the modulus of U drops below 1/2. Okay, that's a reasonable place to think about what a vortex is. So that's outside of the superstate. In superconductors, there's lots of special things that happen. you're not just in a superstate, but also magnetic fields are able to pierce through the sample. And formally, if you look at this energy, then, and epsilon, let's say, is small, so we're really, let's say, in superconductors, we're really far in the type 2 situation, then the modulus of U wants to be close to 1 everywhere. Okay, that was going to make energy small. And in fact, if you say that the energy is reasonably bounded, then that potential forces the set for which this should be less than, it should be included in, let me write it, that's not really what I want to say. It should be this, that the set where U, let's say, is less than 1/2, is inside of a collection of balls. Okay? And the sum of their radii are going to be small. So they're, at first glance, it's in a small set. Okay. But we know, again from the lectures of Leah, that vortices carry additional information. They're not going to form just because. They're going to form also because there's some sort of topological obstruction. Okay. And in this case, it's going to be the degree. So let's say that we're looking at a typical vortex. Then for all radii outside of some small distance from the center, then the winding number or the degree is going to be an integer. Okay? And so this is an important difference between classical fluids and, let's say, superfluids. Here, the degree is quantized, whereas in classical fluids, it can be any number. And so this is our prototypical image. It's kind of like a clock face, right? It goes all the way around. The number of times it goes around is the degree. And that just comes out by the fact that we're using this complex order parameter. This is our typical profile. So to compensate for this clock face, so if we just have, for instance, e to the I theta, it's not in H1. So it's not going to have bounded energy. So we have to use another fact or another feature, which is that the modulus will drop down. So here we have U is rho e to the I theta, let's say for a typical vortex. So if this was not there, it's not in H1. So here we're going to drop down to compensate for this problem. And this distance for which it drops down, and epsilon is some small number, it's going to be on the order of epsilon. Okay, so that's at the center of the vortex. Okay, so this is our picture. And vortices carry large energy, although, log of epsilon may not necessarily be a big number, but here we're assuming epsilon is beyond anything we can imagine. So a giant number. So then this is going to be a distinguishing length scale. Energy is big at each vortex. And so in leading order, if we have, let's say, d vortices, okay, this is not quite right. Let's just assume d is plus or minus 1 here. But so let's say at leading order, then that's going to be our energy. And this is our typical profile. So when you look at local minimizers, this was the beautiful result of Betwell, Brizis, and Hélène. Then we can basically think about these nice equivariant vortices glued onto different locations, separated, and around each of these point locations, AJ, this should be AJ, then it looks like a bunch of clock faces at the center of which the modulus drops down. And so if we have, let's say, 3 degree 1 vortices, then this is going to be our picture. And this size where it drops down, again, is on the order of epsilon at the center. Okay, but this picture is quite generic. It's not just a picture for minimizers, but it's also for a sequence of critical points, and even for any U with a particular amount of energy. So that's a very important and deep result of many different people, including Etienne here. And so this gives us a generic picture, which is nice because when we want to look at dynamics of objects with a particular Ginzburg-Landau energy, we don't need to look at minimizers, right? We don't need to look at an adiabatic limit. We can throw down a U with a certain amount of energy. We know its picture in rough sense. Okay, so this was an important achievement. Okay, so So we need a good way to measure where vortices are. And a good way to measure it is by using the Jacobian, which is the determinant of the gradient of U. And it's a local covering of S1 in some sense. And so if you look at a Jacobian, for instance, of x over mod x, which is, let's say, this e to the I theta with no rho, and you just go through the calculation, then this pops out a pi delta 0. So it tells us that there's a degree 1 vortex at 0. So there's a good measure of a vortex. And so, for instance, if we have U and we want to check how close it is to a bunch of vortices, then we want to have some topology that picks it out. And so a good topology is this flat norm, W minus 1, 1. And if we look at this and we want to say that U looks like a bunch of vortices, basically this picture that we saw before, I'll just go back. If it looks like this, and let's say the centers are really, really small, then we should use this topology in particular. If we have, let's say, 2 clouds of vortices and we measure it in this norm, then it will pick out the smallest intervortex distance and sum them all up. Okay? So if this is small on the right-hand side, then we know these clouds of vortices are close to each other. Okay? In the sense that we can visualize. Okay, but there's even more information in Ginzburg-Landau, which is different from fluids, which is that we have a very tight expansion of the energy. So, for instance, if we have n separate degree 1 vortices, then we have this leading order picture that each vortex carries pi log epsilon plus a constant amount of energy. So there are n of them. So this is our leading order big term. And then there's a second order term, which is an interaction energy, a Coulombic interaction energy. And then we hope, if things are well set up, something that's small. Okay? So here, this gamma naught is a universal constant that arises in the work of Betwell, Brzezis, and Len. And this W is, again, called a renormalized energy, and it just depends on the position of the vortices. At leading order, let's say, if there's no boundary, then it would just be the Coulombic free energy, if they're all degree 1. If there's some boundary, if it's on a bounded domain and there's a particular boundary condition, then boundary terms arise, and those can also be kind of semi-explicitly represented. But again, they just depend on the location of the vortices, and let's say the domain. Okay, so the question then is, what happens in the dynamic setting? Well, I want to look at cases where this Ginzburg-Landau energy pop up as a fundamental feature. So the first case is the Gross-Piasecki equation, which models superfluids. I mean, whether or not to a very high degree, or it is certainly a first attempt to model superfluids. And we've already seen some beautiful connections between the Gross-Piasecki equation and fluids in Fabrice's talk. It also pops up in Bose-Einstein condensate problems, although with a slightly different energy. I won't go into that. But then also in superconductors. This is the Gorkov-Eliashberg equation. And here we can see it's maybe more complicated than the energy that was talked about before. But here we have a coupling between this order parameter and magnetic fields, and induced magnetic fields and induced electric currents. And I'll talk briefly about that towards the end. We won't be working with such complexity here in this talk. And even in more complicated models, as was talked about by Valerie, for instance, Yang, Mills, Higgs, these are all cases where you have an order parameter or pairs of order parameters, and you want to understand when you're in certain states and when you're not. Okay, maybe it measures where a fundamental particle is and where you're not. Don't have a fundamental particle. Okay. So let's talk a little bit about superfluid equations. So again, this is modeled by the Gross-Piasecki equation, which is popping out a complex valued order parameter. And in this case, when we're in the superstate, we're a superfluid. And when we're 0, we're in the normal state. And being a superfluid means there's no internal friction. So if you spin it, it should spin forever and do some other crazy things. So in this case, we want to understand, for instance, if we pop down a couple of these vortices, how are they carried along? If vortices move, how do they move? If so, where do they go? And this has been studied a lot. It dates back even to the 60s, and by Nu and E in the 90s, that in the limit, the Jacobian of U is going to condense down to a bunch of point particles, meaning we have a bunch of degree 1 vortices, and they will be carried along by this very simple relationship where W, again, is the Coulombic free energy. In other words, we get the point vortex motion law that we saw earlier in several lectures. We get the Helmholtz-Kirchhoff ODE. So there were some rigorous proofs by Colliander-Girard and Lin and Shin for a finite number of vortices. And I'll talk a little bit more about that in a bit. But how do these move? Again, this has been covered in many lectures. If we have 2 degree 1 or 2 minus 1 vortices, they rotate around each other. Basically, if we think about this particle, it's going to be carried along by the current generated by the other particle, and that would be pulled around in a circle. And again, a plus 1, minus 1 vortex will be carried along by each other's induced current, and that again would cause them to go in parallel. Okay, so let me just review again. So there are rigorous results by Colliander-Girard and Lin and Shin for bounded, simply connected domains, for a finite number of vortices, and finite times until collisions, and for well-prepared data, meaning that this only works if you have just the right amount of data, not too much excess energy. Otherwise, the technology breaks down, and this was also discussed by Fabrice. Once you have too much energy in these methods, we don't understand what happens. You could have waves that come in and jiggle the vortices and do things that we don't really understand. And in fact, you could cook up really bizarre things in which you could have very close dipoles coming in towards a vortex and really push. That looks like a small amount of energy in some sense. You go a dipole, small amount, but order 1. But really, they're basically like a pair of vortices come in and jiggle a vortex over here. So it's a non-trivial question, what can happen when you have excess energy? And so this is a very important assumption. So, and then Bob and I looked at what happens if you can improve this. In particular, we want to know what happens when you get large numbers of vortices. And I'll talk about the motivation for that in a bit. For asymptotically large numbers of vortices, for asymptotically large numbers of time, for asymptotically large times, but also for, again, well-prepared data because we are way far away from understanding this problem when there's too much energy. Okay, so that is the Gross-Pitevetsky equation. The other equation I'm going to talk a little bit more in depth about is an analog to the superconductivity equations called the Gorkov-Eliashberg equation that I presented before. But here I want to look at a simplified analog that I will not call a model for superconductivity, but maybe a model for the phenomena that comes up in superconductivity. So if we want to do the full model, we need to couple this to an applied magnetic field equation. So again, in this case, that should not be superfluid. So in the superconductor, if we're 1, we're in a superconducting state, meaning there's no internal resistance to the motion of the electron. And if we're 0, then we're in a normal conducting state. And in this case, you have to wait a little bit for vortices to move on the order of log epsilon. And then you get, instead of the gradient curl, you get the gradient of the energy, of the renormalized energy. This is the steepest descent. So in this case, vortices are pushed away if they're the same sign, and they are attracted if they are of opposite signs. So we expect vortex annihilation if there's +1, -1, but vortex, +1, +1, we expect things to be spreading apart equally. And in this case, there are rigorous results by Lin and Girard and Sohner, and especially precise results by Serfati and Batuel, Orlandi, and Smets. Okay, but in this case, in superconductors, in type 2 superconductors, we see lots of vortices. We don't typically see one isolated vortex in a sample. We typically see large arrays. And so this was first uncovered analytically by Vrysokov, but there are actual experiments where they see huge lattices of vortices. And this discussed earlier. But you can imagine there being huge numbers of vortices. I think they're on the order of maybe 10 per square micron. I mean, when I've taken a ruler and counted them on a picture of the first images of superconductors, there may be 10 per micron, square micron. That comes out to a lot of vortices. And so, what happens in aggregate? When you get lots and lots of these vortices, is there some sort of collective behavior of the vortices? So what happens in a dynamical setting? So this was talked about, and will be talked about by Etienne. When you have a big lattice of vortices, how do they behave in a static setting? But you can also ask what happens in an ensemble sense when they are in motion. And so this is also some experiments from maybe 10 to 15 years ago where there are lattices of vortices and they are driven by electric fields. You can see some really interesting things. And so there were some results by Chapman, Rubinstein, and Schatzman, and by Weinan-Yi in the 90s that imply by some formal arguments that there's a mean field behavior for these equations, for these vortices, right? Just as in the point vortex method, there is some sort of collective behavior of these point vortices. Now you can ask what happens in the superconductors and superfluids when there are large numbers of vortices. So we have an ODE description for asymptotically many vortices, but is there a mean field description for the number of vortices as they get bigger and bigger? There was a result of Lin and Zhang that there is a proof that if you look at this ODE on R2 and let n go to infinity, where this J index goes from 1 to infinity, 1 to n, and n goes to infinity, then they derived a mean field equation for this. And I'll talk a little bit about that. But can we fully justify the limit of this parabolic Ginzburg-Landau, so this analog without the applied magnetic field? Can we justify the limit to this mean field model and in some sense have a consistency statement so that if we have some type of, let's say, weak initial data, that we can construct solutions that are approximated by vortices and then evolve according to the mean field equation? Yes? Yes. So they're basically using the same technology of Delors and Maida and so forth. So, yes?
What is collective behavior when there is a lattice?
If they're already in the lattice, then there isn't anything that's too interesting. Although I'll explain a little bit of what my result, which is not so interesting at this point. But when you start adding applied magnetic fields, then things can be very interesting. And we haven't yet done that. So I'll talk a little bit about that. Okay, so this is the only bit of math that's going on, but I want to give you some idea about scalings and how this argument works. So I didn't even define what omega n is. So really we want to understand some vorticity measure. Omega n will be the summation of aj of t, right? This is my delta function aj. And that's going to blow up, right? So we need to renormalize it in some sense. So we divide by n, and we want to know how this evolves. So when this is locally 0, right, that means there are not that many vortices in that area. When it's getting big, and let's say if it's close to 1 at some spot, that means they're all aggregating in one area. Okay, so it's gonna it's in some sense like a fluid or like a gas. Okay, so if you just multiply by a test function and integrate and take the time derivative, so you could ask, this omega n should converge to your limiting vorticity measure, or your vorticity density measure. So I added a 1 over n, and we'll see why that's important. Okay. So if you just follow through, this is a delta function, out pops a time derivative of aj, you plug in the ODE. Okay, this is without boundary, let's say in all of R2, formally. And then you take the derivative, you get this equation right here. And then now you pull out, formally, let's say, it should be integration in x. Then you can write this ak then as a delta function in x. Okay. But then this delta function can be written as the Laplacian of the log of ak minus x, right? And now you can integrate by parts in this, and you get this equation right here. Okay, so this looks very formally like the calculation we saw earlier for the Delors method for showing weak solution. But then what you can do is you can pull these AJs and these AKs, again using delta functions right here. And so we see if we want to divide both of these objects by n, then we needed to have a 1 over n over here, because otherwise we would have had just 1 over n. Just 1 over n. Okay, and these guys are the vorticity measures. So you can see that these guys are limiting to the right thing right here, and this looks exactly like our equation we had before. But there should be no perps right there. So then you can ask in the limit, if time is rescaled, right, then you would expect to get a fluid equation popping up. Okay, and that's what we get. So this is the result. So here the idea is that we want to go. So some things are already understood. So here we have parabolic Ginzburg-Landau, which I'll write over here. Again, just a model for the true superconducting behavior. And then we have an ODE. Okay? So if we have, let's say, localized vortex structure at a couple points, this has been well understood when n is finite. And then we have a mean field equation. So there's the collective behavior of lots of vortices. Okay. So this was understood when n is infinite. Let's say n goes to infinity. This is n less than infinity, right? So there's an issue, right? So if you want to say, I have a Ginzburg-Landau set up with initial data that looks with epsilon so that the number of vortices scales asymptotically large with epsilon, then how do you get from here to here? Okay, and this is a setting that we see, right? Because, you look at the experiments and the number of vortices are scaling asymptotically large as epsilon gets small. And so here, this is what we want is n to go to infinity as epsilon goes to 0. Okay, so this was the issue that we had. And so we're able to do that. But, this is a problem, right? I would say that that's a finite number. But, to mathematicians, that's an infinite number, I guess. But in some sense, we are able to do that. So we can take any probability measure such that its h-1 norm is finite. So vortex sheet initial data. We can then build initial data from that. Okay, so such that these point vortices converge to this initial data. And this itself is an interesting problem because we want to approximate any vortex sheet initial data with quantized vortices. So if you do it in the classical fluid equation, you can stick any number on these delta functions. But here we have to use only quantized vortices. So we have to kind of, take any value approximated by subclusters that converge to the particular value that we want. So this itself is kind of an interesting question. How do we converge here such that, its energy is in some sense finite? And then we look at this energy measure. So this is going to converge to delta functions, right? Because the energy is concentrating at the site of the vortices. And we rescale by n, so that handles this time rescaling that we needed. And then in the limit, this omega tilde converges to a weak solution of this fluid equation. So if this was a classical fluid, then this would be a perp here. This would be a gradient perp of the Laplace inverse. I think there are too many minus signs here, but I'm not sure. And so I want to talk a little bit about this equation. So again, here we are constructing initial data from these point locations. Epsilon is a small parameter from the Ginzburg-Landau energy. So. Yeah, because we want it to be getting bigger as epsilon gets smaller. I'm sorry? Super slow. That was the rate is there. So n is, yeah. So it's not great, but I mean we would want to have it on the order of log epsilon as opposed to log epsilon to a power, right? It's almost embarrassing to say, but here the energy again is the only thing that really depends on epsilon. Okay, so that's what's giving the length scalar. So it gives you the size of the vortex and the energy. Okay, so this is just explaining what this Laplace n inverse is. Basically the inverse of the Laplace of the Poisson problem with particular boundary data. That's sort of sometimes degree 1. But I want to explain more about what this fluid equation is in this case, which actually is interesting. So if you just formally differentiate, you get this equation right here, but the divergence of u is the divergence of the gradient of the Laplace inverse. So that's the Laplace of the Laplace inverse. They annihilate each other, and out pops another omega. And so what does that tell you? Well, along the trajectory of the flow, omega dt of omega equals minus omega squared. And so the vorticity is decreasing. So this is different than in Euler. Euler, it's conserved. Here, the vorticity is dropping like 1 over t. Okay? Again, this is kind of strange, but I'll try to explain what this means also. By the way, this only works on bounded domains, so I will explain that. So in some sense, it's a dissipative Euler equation, whatever that means. But more importantly, what does it mean? It means that all I'm looking at are test functions that are active in the interior of my domain. And that is where things are decreasing. And so that means that vortices are being expelled towards the boundary. Okay, so this is a feature of the Ginzburg-Landau problem when you have high degrees, as n goes to infinity, vortices are going to congregate on the boundary and not in the middle. And this is the result of Sandé and Sorel. So this basically tells us something about maybe the mesoscale or the intermediate times of the evolution of this liquid, of the large aggregate of vortices. They're being expelled towards the boundary. Okay, so what about in Gross-Pitovetsky? So Gross-Pitovetsky has a stronger correlation to classical fluids, and I'll try to explain that. So just to go briefly, there have been so the question then is, can we show that Gross-Pitovetsky converges to the Euler equations, as the number of vortices go towards infinity? So the results of Bob and myself said that, well, you could study Gross-Pitovetsky on bounded domains with asymptotically large numbers of vortices. But that's a problem because the ODE behaves poorly on bounded domains, because as you get towards the boundary of the point vortex method, you get a ghost particle coming towards it and things can speed up. It's not being repelled from the boundary. Things can happen that are strange as a vortex approaches the boundary. And we need vortices to stay away from the boundary for times of order 1 over n, which sounds small, but larger than non-trivial. So there's a failure both of the PDE and ODE methods and the ODE to PDE methods if you're looking at bounded domains. So we wanted to consider Gross-Pitovetsky dynamics in all of R2 with asymptotically large numbers of vortices. So we can use ODE to PDE technology that's already well known. The results of Chauchet, Maida, Evans, Mueller, all these, it's well-defined stuff. So the results on all of R2 for a finite number of vortices by Betwell, Gerard, and Smets. But we need n to go towards infinity as epsilon goes to infinity. And so this is the result that we can show that for any vortex measure with finite first moment, with first moment 0, and n is scaling at a slightly better rate. So log of epsilon is better than log of epsilon. Then these vorticity vortices are going to converge to omega naught. If their energy is finite, then we can construct data such that the rescaled vorticity converges to a weak solution of the Euler equations with that vorticity, initial vorticity. Okay, and this is some topology that's related to this flat norm that is better behaved for us, but morally like the flat norm. So let me just explain a few notes about this, and then I think I'll be finished. So there are a couple interesting problems that come with this. First of all, as was noted in a couple places, a vortex is not in H1 on R2, okay? Because it decays like 1 over R. Is Grotz-Pitaevsky even well posed with vortices on R2? I mean, if the energy is infinite, how do you come up with a well-posedness theory for infinite energy? Well, there was an important result by Betwell and Smets, who developed a theory for global well-posedness with vortices, so a kind of infinite analog. So what do? You basically subtract off an equivariant map of degree d, where d is the winding number of everything at infinity. Okay, and so then it can kind of renormalize the energy. This E kind of makes sense, right? And also that they show that this energy is conserved, that this renormalized energy is conserved. This is also very important. So it has a kind of a Hamiltonian structure also. And then Betwell, Girard, and Smets use this to prove the motion law for a finite number of vortices for finite times. There's also something by Lin and Shin for degree 0, but we want degree to be going towards infinity. So the proof follows from basically differential identities for the Grotz-Pitaevsky equation. Again, this is the Madelung transformation, but not yet reduced down because we don't want to be too careful, or we don't want to be too reductive at this stage. This is like conservation of mass, conservation of energy, and conservation of vorticity. And from those, you get everything you need. And the idea, since we want to know what happens as epsilon goes small, we need quantitative estimates on everything. Quantitative estimates on how close U is towards 1. Quantitative estimates on how close the Jacobian is to a bunch of delta functions. And quantitative estimates on how close U is to the limiting U profile away from vortices. And then the idea then is to renormalize lots of different things. We have to renormalize the vortex core because that's blowing up. We have to renormalize the degree at infinity because that's blowing up. And then we have to renormalize the number of vortices because that's also blowing up. So there are 3 things we're simultaneously renormalizing all at once to make some connections between these 2 things. So this is the flavor. So again, going from the ODE to the mean field equation is what's well understood and kind of classical. The question then is going from the parabolic Ginzburg-Landau or the Schrodinger-Ginzburg-Landau to the ODE. That means understanding these phase transition equations with asymptotically large numbers of vortices. And this is the kind of the flavor of the result that we would need. And I won't go through the proof, but it says, well, suppose we have J, the initial data that's concentrated close to a bunch of delta functions in, let's say, the flat norm. Okay? And we know it to a high degree. So this, again, says that it only works for well-prepared data, as was discussed. And N is, big, but, not too big. And that these vortices are not too close together, but can be close. And suppose that this energy that's renormalized at infinity is close to kind of a perfectly constructed profiles. Okay, that's also close within epsilon to the 1/2 resolution. Okay, then for all time, the evolution, up to a certain time, the evolution of J of U is going to be close to the evolution of these vortices in the same flat norm, up to, again, a reasonable resolution. And this is valid for times that are defined implicitly, but we can estimate this in a lot of cases. The hydrodynamic limit follows from Chauchet. Okay, so that's the flavor of the results. But again, maybe the physics is not as present. One thing you can do is try to add some other things that maybe better model what goes on in superconductors, you can look at generalized Gorkov-Eliashberg equations, which no longer are gradient flows. And these were proposed as more reasonable models. There are also models that include pinning that Valerie described, and he knows a lot more physics than I do. And you could ask then, what happens as you turn on applied fields? As you turn on electric fields, then you can ask, what do the liquids look like? These vortex liquids. Those are things you could possibly measure, and then try to go back and recover your physical constants alpha and beta, maybe from the behavior of these liquid equations. It's not so challenging to formally derive what these liquid equations would look like from this, based on the what is known going from here to here, and then formally what's known going from here to here. But getting large numbers of vortices into these to behave well enough would be more of a challenge. And then also, what would happen if you include other interesting physics, like adding stochastically driven noise and other things that come up in the real physics. So, and thank you.